Hey,
Hi,
how are you?
good. How are you?
Good.
Good.
Your camera looks clearer.
It does?
Yeah. Did you get a new computer or is that a
Yeah.
different computer? Nice.
I thought you were going to post a video for Calc and you.
I was just gonna go through it together and then record that.
Alright.
Same for here. I lost track of the time, so I was a couple minutes late on starting this. Hi,
Hello.
how are you?
Good. How are you?
Good. Hi. Hello. Hello, everybody. Um, so we'll wait a minute. I was a little late starting the classroom. Hello. Hi. How many people we got? 13, right? So with me, that should make 14. We'll just wait a minute more. How's everybody doing?
Amazing.
Impressive. There you go. I'll wait a little bit. I guess we are missing. Well, I think Andrew might not be here.
He's not coming, Bri.
Yeah, I like skipping school.
So we're
No, he's
missing.
probably baked off getting his wisdom teeth out.
Who are we missing?
That's what they all say, Brady. That's what they all say.
Emma. Okay. All right. Well, today we're just going to do a bit of kind of review. I'll just remind you guys kind of what we were up to when we left for break. And we'll go through some questions, I guess, from last semester. Make sure you guys are still able to do those. I've got a short little video. I think I posted it already to the My Open Math. Yeah. So after this class is over, you can go to My Open Math for the stats course. There's a new block underneath the probability block called inferential statistics. It's above all the practice assignments. And there's like a video that's less than 3 minutes long. So it's just, it'll probably communicate all the things I try to communicate in this class in under 3 minutes. So I'd recommend you watch it because it's got nice visuals. So how was everybody? How was your break?
Solid.
Good. So awkward doing the remote class. You can ask like this really big question and like about like life and stuff, and everybody just be like. Anyway, so I guess we'll get started. I'll present my screen and yeah, we'll do it that way. right. Can you guys all see the MyOpenMath page?
Yeah.
All right. So when you're here, let me know if you can't remember how to log in or something. But you should be able to just hit inferential statistics, and then there's the video here. Watch that later, though. Let me get on my tiny little glove here. I'm going to give you some visual aids. What? It's never done that before. There we go. Can you see that okay? Okay. So I tried to do some dot plots and then use the little highlighter to make a little outline of a normal distribution fit to that data. So just to kind of remind you, here, if you can see the little green dots up at the upper left, can you guys see my cursor moving around?
Wait, move it.
I'm moving it.
Oh, then I'd say no.
Okay. I've noticed that about Google Meet is it hides the cursor. So I don't know if there's a setting for that. Let me see. Hold on. I do want you to see the cursor. I have no control over that, I think. Anyway, all this time I've been like indicating things to you guys with my little cursor, thinking you could see it, but I guess you can't.
Yeah, I had no clue what you're doing. You're like, yeah, watch this. I'm like,
I think you can, because Mr. Olson got it to work, and like he was using his cursor to like show us stuff. So I don't know. I think there's
Can
like a
you see it
way
when I move
you
the
can like
mouse?
turn it off in settings.
Can you see this?
Mr. Olson's
What?
also a tech wizard.
Can you see?
Yeah, we can see that. Yeah,
You can see me circling the upper one.
it's really fun. Mm-hmm.
Okay. So I guess if I use my mouse, it works, but not if I use my little pen. That's weird. So you'll see the little data points at the upper left one. Hopefully you can see them somewhat clearly. That kind of represents the data. And like we've talked about like the height of trees, because I'm really good at coming up with examples. So, you know, these could be the height of adult trees of a certain species in Sterling, maybe. And this represents their heights. They are clustered around some average value. Most of them are close to that average value, but there are some that are much shorter and some that are much larger, but not as many as are near the average. And that was our normal distribution, right? Does that all ring a bell? All right, I'll take that as a yes. Then with the yellow highlighter, I kind of made an outline of the normal distribution of that, which is a model that we fit to the data. So what we need in order to do that fitting is a statistic about, I guess I'll use blue. So in order to make our normal distribution model, we need to know what the average is, what the mean value is, and we need to know what the standard deviation is. And if with those two, which the mu is kind of like where it's centered, and the sigma kind of tells you how wide the distribution is, how spread out. The bigger the sigma, the bigger the standard deviation, the wider the spread. So remember, standard deviation is kind of like the average distance from the middle. So if that helps. And then what I have right below that, I don't know if you can see that well. It's another normal distribution. It's supposed to be the same kind of normal distribution, but some of the green dots are orange. I actually made 13 of the dots orange. Does that make sense? Or can you see that?
Wait, why do you make it orange?
It's representing, like if I picked 13 trees at random, those would be highlighted. So I've selected a sample from the population.
Oh, okay, I got it.
Does that make sense to everybody?
Yeah, that makes sense.
Okay, so I have the population, and I picked 13 at random, and I've showed them highlighted. Hopefully you can see that. Now, I could have picked any 13. So there's, I don't know how many dots I put there, but if you take that many dots and you find out how many combinations of 13 there are, the number would be huge. You know, like it'd be a tremendous number of dots, you know, like, or sets of 13 that you could form. There's, you know, thousands and thousands of different sets of 13 that you could imagine having as your sample. I've just shown one. Does that make sense? Okay. I'm distracted by your balloons, Marisol. So those 13 that I've highlighted, I don't know if you can see down in this one down here, well, you probably can't see the cursor. Can you see my cursor pointing down at this red distribution?
Yeah.
Do you see how like one of them is colored black?
Yeah. Why is that? Because it's different.
It is different. That one, I don't want to read while you're eating.
They're so good, I can't stop.
So if I select the 13 orange trees and I average their heights, notice that I have almost just as many dots on the left side of the middle as I do on the right side that are orange. And that's typically and that represents, you know, I might have a few more on the right. So I put the dot a little bit on the right. But if you averaged whatever values, whatever X values, you know, you had for those orange dots, they would average pretty close to the middle. You know, they're pretty fairly spread on one side and the other. And so I got a dot that averages somewhat close to the middle, maybe a little bit to the right. So I colored that dot black to represent this sample that I've selected. Does that make sense to you? Good. So what the red distribution represents down below is every conceivable, the dots represent the average value for a sample of 13, and the whole set of dots represents every conceivable set of 13 that I could possibly assemble from the population of trees. So however many sets of 13 I could make, I've plotted their averages for those 13 in the red. And the idea here is that when you draw from random from the population, you're always just as likely, it's like flipping a coin. If 50% of your trees are on the short side and 50% of your trees are on the high side, getting a short tree and getting a tall tree is like getting heads or getting tails. They're equally likely. And so if you flipped a coin 100 times, you're very likely to get something close to 50 heads and 50 tails. It's almost impossible to get 100 heads. Right? It's very unlikely. If you think of how many ways there are to get 50 heads. There's only one way, and that's when every coin is heads. I'm sorry, 100 heads. If I flipped 100 coins, there's only one way I can get 100 heads, and that's if every single coin came up heads. So there's only one of those. But the number of ways I could have 50 heads and 50 tails is huge, because the first coin could be heads or it could be tails. The second could be heads or it could be tails. There's so many ways I could have 50 heads and 50 tails arranged that they're far more likely. There are far more ways of having that than there are of having it otherwise. The idea here is that when you sample, your sample is very likely, it's very hard to get a sample that's distant from the mean value of the population, because you usually draw almost just as many from one side as you do from the other side of the distribution. So when you plot, if you were able to come up with the mean value of every possible average value for any 13 trees, if you plotted those, they're going to be even more tightly clustered around that mean, because it's very hard to get away from that mean with an average of 13. And so when I make so up top, this represents my population distribution. That normal distribution that I model it off of, I take the mean value, that gives me the center of the distribution, and the standard deviation for that population tells me how wide to make my normal curve. And when I plot the values of a population, the axis is a capital X. And the capital X represents picking one thing at random out of a population. So that represents a random case in the population. So here's a value of X, capital X. It's not like algebra. You use a capital in statistics or probability. But when you come to the sampling distribution, which represents the average value of 13, each dot represents the average value of some different set of 13 trees. We use X bar because it represents an average now, not the value of a tree, but the average of 13 trees. So we put a bar to represent that this is an average. So this is each dot represents a randomly chosen sample in the whole sample space of all possible samples of size n. And in this case, I chose 13 dots. Are you guys following so far?
Yeah.
Okay. So in order to model the sampling distribution, again, you would just make a normal curve. You would use the same middle, because these things don't change the middle. They're still clustered around the population's average. But for the standard deviation for sample means, you take the population mean and you divide it by the square root of the sample size. And that shrinks that, that makes a smaller standard deviation. And that's how you make the normal distribution to model when you have a sample. In this case, if n were 13, I'd divide by the square root of 13. And I put that into my calculator when I did the normal CDF and when I did the inverse normal. Otherwise, it works exactly the same way as the problems that we did with the normal curve. Is that ringing a bell?
Sounds familiar.
Good. Yeah, we're just reviewing, All right. So now we have different symbols for this, this thing here. I'll do a different color still. One symbol for this is the standard deviation of sample means. So sigma sub x bar. Like on your calculator, like when you do one variable statistics, it calls sigma sigma x, which represents the standard deviation of the population of individual cases. And this thing is defined as the population standard deviation divided by the square root of the sample size. So sometimes it's called the standard deviation of sample means. So you'll hear that term, you'll see that symbol. It's also called the standard error, which I usually call SE. So you'll see it by both names, both symbols. Different authors will use different symbols, so just try to understand the concept more than anything. The standard error is good job, Nate. Is the standard deviation for a sample distribution. There are other sample distributions. So if I did n equals 100, I'd have an even tighter, I can't even draw that one. I'd have like an even tighter distribution if I did n equals 100. So there's different types of sampling distributions you could have. They depend on the size of the sample size, the size of your sample. But that's how they work. Are we okay on that? Any questions? Okay. So let's try some questions from last semester. I'm just going to open up the sampling distributions thing, and we'll go through this together in class. Do you guys have your calculators? Nice. Okay. Whoops, that's not what I want to do. Click it. Teacher preview. Can you see okay? All right, question 1. A population of values has a normal distribution. So this is a population of mu equals 241.5, and the standard deviation is 25.4. You intend to draw a random sample of size n equals 206. There's 2 questions. Find the probability that a single randomly selected value, so sample size of 1 here, find the probability that a single randomly selected value is greater than 242.9. You guys know what to do?
Will, how do you get that?
Wait, do you use normal?
What'd you say?
Me?
Either of you.
Do we use the normal CDF?
Yes.
Okay.
Well, I think Will got it. Did we get that? Can you show me your calculators? Kidding. Okay, so then the next question is find the probability that a sample mean of size 206 is randomly selected with a mean value greater than 242.9. Nate said something. There you go. Reward yourself with goldfish.
They're not goldfish anymore. They're flins. Just so you know.
Flins?
Yeah.
I don't get that.
The guy's name is Finn. It's on the box.
Oh, okay.
I could show you, but like, it won't work.
Well, I can see. I'm presenting a different screen, but I can still see the tile view. I don't see. Oh, it does say. Is that under his body? It says Flynn. Okay.
So it's Finn now.
Oh, Finn.
Yeah, Finn.
Anybody have any questions on this one? Okay.
Wait, how do you do the sample size again?
The what?
Like when it says the sample size, don't you have to divide that by like
Yeah.
the square root of something?
The standard deviation you would divide by the square root of 206.
Oh, okay.
So yeah, for this one, you're going to choose for your normal CDF. Your lower bound would be 242.9. Your upper bound would be some very large number. Your standard deviation would, your mean would be 241.5. And in the first problem, your standard deviation would be 25.4. But in your second problem, you would divide that standard deviation by the square root of 206. And that should give you those answers. Is that good? All right. Question 2. A manufacturer knows that their items have a normally distributed length. The mean of those is 5.1, and they have a standard deviation of 0.6 inches. If 23 are chosen at random, what is the probability that their mean value is less than 5.1? What are my bounds going to be? What's my lower bound going to be?
Just like the negative 9999.
Yeah, that's right. It'll be negative, something big. Yeah, that's an easy one, isn't it? You really don't need a calculator for this one, I guess. If the middle point of symmetry is 50 or 5.1, what's the probability that, that they'll be less than 5.1?
50%.
Yeah, right? Just one side of the middle. Yeah, good. So that one's kind of, you could do it, it'd be easy, but you could just think about it and know. Does that make sense to you guys? Okay.
Yes.
Okay. I might be losing you guys because first only Nate was moving and now Skylar's moving. Now Nate's moving it. Everybody else is like frozen. Now I'm seeing people slowly come back. Okay, 3. A particular fruit's weights are normally distributed. The mean's 202 grams, standard deviation is 33 grams. You pick 11 at random. What's the probability that the mean weights will be between 224 and 235? Anybody got it?
I bet Jordan has it.
Pressure's on, Jordan.
Is it the 0.013059?
Yeah.
Oh, that is not what I got.
What did you enter?
What?
I did 224 and 235 for my lower and upper,
Yeah.
and then 202 for my mean, and then 33 for my standard deviation.
Nope. You want to divide that by the square root of 11.
33 divided by that, right?
Yeah.
Okay.
Yeah, Brady, now you're on to it.
Is that good? All right. Let me try one. Let's try 5. The manufacturer knows that their items have a normally distributed lifespan with a mean of 4.3 years and a standard deviation of 1.4 years. If 7 items are picked at random, 4% of the time their mean life will be less than how many years? This one's a little different, right? $3.4. Yes.
Yeah, actually, that's what I got, but
What was different about
Isn't
this?
this one where like if it says less, do you have to subtract or do you keep it as the 0.04?
inverse norm.
Yeah, but isn't there like don't you have to like subtract it from 100 at a certain point? Like if it says greater or less?
If it's on the left, you enter the area as it is. So 0.04. If it was greater, you would do 1 minus the 0.04, like 0.96. Does that make sense?
Yeah, it does. I just forgot which one it was.
That's good. That's okay. Very good. What's 6? Yeah, how about 6 then, Jordan? That's that's kind of like that.
Pressure's on now, Jordan.
A particular fruit's weights are normally distributed. The mean is 541 grams, standard deviation 17. 19 fruits were picked at random. 9% of the time, the mean weight will be greater than how many grams? So if 9% is above this mark, what percent of the time, what percent are below this mark? Let's see. Hey, there you go. Does this all make sense to you guys? Good, good. Okay, so you guys are good with that. Whoops. So,
I think we could call it.
Yeah, I had to
Tell us.
be late on that one. Just call it a day. It's been a long one.
we're just reviewing, guys.
Hmm. Yeah, but Brady has been in school for like 3 weeks, and I already know his head's hurting.
You can
Just
are
it's
you guys
spinning.
linked? Can
Wait,
you-
what?
I might have to leave a little bit early from the meeting because I have to go to WAC
Okay, yeah,
and I like live far out, so like I drive out there.
that's okay. Well, I just want to go over a few more things. Shouldn't take too long.
Okay. Yeah, that's fine. And then we can play. Then we can throw in the towel and play some poker.
Virtual poker.
Physical.
All right. Here go my drawings. So remember that, like, if you have a mean value of, let's say, 100, standard deviation of, I don't know, 6. What would the z-score be for the value of 89? How would I calculate that? You guys remember the formula?
Wait, the z-score formula?
Yeah.
Isn't it like mean minus or no, it's like the critical z-score minus the mean or something divided by the standard deviation?
Almost. The value minus the mean. Divided by
Oh
the
yeah.
deviation,
Okay.
yeah. And that gives you the z-score. Yeah, good. So yeah, I would take 89, right? I'd subtract 100, and that'll give me a negative value because I am to the left of it. And then I would divide that by 6. So I'm counting how many steps of size 6 I am from the middle. And if it's negative, that means I'm to the left of the middle. So what does that come out to be?
Negative 1.83.
Yeah, good, good. So that makes sense to you guys? Good. And then you remember you have your critical z-scores that were associated with different confidence levels. Those were, hold on a minute. Yeah, so we can hold off on the confidence intervals till next time. But yeah, so you're good with Z-scores, and you're good with your standard error, your sampling distributions. Next class, we'll review confidence intervals and then pick up from there and start moving on to new stuff. Sound good?
It sounds amazing.
Any questions?
So wait,
Yeah,
we're doing this next class, the confidence level.
confidence intervals, yeah.
Yeah. Oh,
Yep.
and can no one else like not see anyone?
It does that when it's presenting.
Well, here,
I could see everyone before, and then now it's like totally bamboozled. Unless you pin someone.
Me too.
I can,
Oh, there's everyone. Oh my!
Off for me.
Ow!
can you see it
Now I
now?
can see everyone's beautiful face. Oh wait. Oh no, I can still see Brady.
Better? Oh, all right. Well, I did record that, so if anybody, was everybody here? Yeah, everybody's here. So.
Andrew wasn't.
I'm gonna go give it a like and
Oh,
comment.
Andrew. How are there 14 people in here?
I'll
I'm
share it with. Oh wait, it's happening again.
when I presented, it adds an effort.
Oh,
So,
there we go.
That's I'll put this onto the same playlist that we used last semester. It's still the same concepts of statistics or whatever I called it. I forget what the playlist is, but it's the same. So I'll post this there after class. Okay?
Got it. Hey, wait.
Yeah?
What sounds good for lunch? Subway, McDonald's, Don Pedro's, or Wendy's?
Altap.
Wendy's and McDonald's.
Oh, it looks like I'm going down that. Sorry, Mrs. Stella.
Well, I mean, there's Willie's, there's Kelly's. You can do carry out of
This is so far.
Waka Nachos.
Papa Nachos. I never heard of that.
Waka Nachos.
Oh, I thought I heard Papa. I was like, oh my gosh, Mrs. Stella.
Tomorrow, I plan on getting an order of the Waka Nachos and a bacon cheeseburger with fries from Kelly's.
Where's that at?
Kelly's is right on the little one-way.
Is that Kelly's? Oh,
Right by Lisa's.
What's that?
Said it's right by Lisa's. Kind of.
Yeah, and the Rusty Fox. And
oh, you go to the Rusty Fox often?
no, actually,
Oh,
I'm too cheap.
Hmm.
And I gotta buy stuff soon, so I'm even cheaper than normal.
ooh.
Even. Anyway, you guys have a great rest of your day. And I will see you when? Friday?
Yeah, I mean, yeah.
Okay. Take care, you guys.
Adios.